Hey everyone, thanks for sliding through. My name's Kyle. I'm currently a research fellow with ERA in Cambridge in Britain, and I'm really excited to talk a lot about the paper that we released, I suppose around this time a week ago, regarding a couple things like how we can make open weight models safer, how we can prevent models from learning capabilities, um, that this is all surprisingly tractable, and lots of other like interesting auxiliary results as well. But I suppose one thing I want to caveat and get out of the way right now is this is like a very diverse collaboration with lots of folks, and my own sort of like hot takes and interpretations, while largely based on like the paper that we released, don't necessarily represent the organizations involved with this work, which include like EleutherAI, University of Oxford, and the UK AI Security Institute. But anyways, I'll start jumping into it. Yeah. So yes, I mentioned I'm currently a research fellow this summer in England. Over the spring, I was contracting with EleutherAI, leading this work. This is where deep ignorance came about. And then before that, I was at Microsoft for a number of years, doing a lot of like applied ML engineering stuff related to trust and safety, content moderation. But then began to get into research on the side as like a hobby, and now began to pursue AI safety research full time, starting this year. And then we released a website alongside our paper, deepignorance.ai. Here you can find a quick abstract of our work, all the link to the paper, all the models and artifacts that we release, some of the code that we used, and also link to various general like news articles that's cover this work, including Washington Post and Fortune. So for more of like a semi-technical audience. So deepignorance.ai. This also includes my contact information and those of my other senior co-author. All right. So minimizing some things. Excellent. So the main problem that we're interested in studying, or well, the main problem that we're looking at is LLMs can learn unsafe knowledge. And once they've learned this knowledge, we can't easily get them to forget it. Um, so what I mean by that, or to flesh that out, is we focus on LLMs. Broadly, the setup is that we pre-train them over much of the internet. Hundreds of millions of documents, hundreds of billions to even trillions of tokens. And this is where they learn much of their factual knowledge and maybe a lot of their underlying capabilities. And this is really excellent. As y'all all know, LLMs are super interesting and really valuable. But along with all these really like economically useful and really interesting capabilities they learn, they can also learn dual use knowledge or unsafe or undesirable knowledge. Knowledge that it'd be kind of convenient for the model providers if these models didn't know. So this being like an AI safety largely audience, like the archetypal examples of dangerous knowledge will be capabilities that might provide like biorisk uplift to low resource actors, so that can be dangerous, or like offensive cyber capabilities, like models knowing how to do hacking and things like that. Um, and these sort of like dual use capabilities, models are increasingly beginning to exhibit them. This is measured by like various dangerous capability evaluations. One example here that I think is a bit representative is that in the chat OpenAI's like deep research like safety card or system card that is, which was released in February of this year. OpenAI talks about, oh, the models are beginning to be on the cusp of like being able to provide like uplift regarding like biorisk. And then in July, so not so long ago, just in only a few months difference, OpenAI states that, oh, we believe this threshold might be crossed, so we're going to take additional safeguards. Now, you might put varying merit into these claims, but one thing that's just like broadly clear is that things are moving very quickly and capabilities are improving, including on capabilities that might be unsafe or just undesirable under according to the policies of the people creating the models. So these models are learning unsafe knowledge. Segueing into another kind of like part of like the context or problem setting we focus on is open weight models. So this whole capabilities improving, including dual use, applies to closed weight and open weight models. Open weight models are those that users can download locally. What I like to do in the in-person talks is to be like, okay, raise your hand if you've ever downloaded a model off of Hugging Face. And almost everyone does, especially if you used it for like safety research. Be like, okay, those are examples of open weight models. Think your llamas, your DeepSeeks, your Olmos, Mistral, GPT OSS, and so on. Open weight models are really cool. I love them. They've enabled much of my research and the research of many safety like organizations. For instance, there wouldn't be much of like a mechanistic interpretability field without open weight models, without the ability for people to download models locally and study them. So they're maximally transparent in that respect. They also have like a lot of like economic, like nice properties that make them useful. For instance, because you can download them locally, maybe they're useful for on-device workloads. And since they're downloaded locally, you don't need to send your data to a company's data center in order to like in the prompts. If you maybe are worried about sending, including sensitive information in a prompt to ChatGPT or another kind of closed model. Now, users can modify them as they wish, and this is really cool, but this also presents a safety challenge. And this is kind of what I refer to as like the core risk or the core challenge in open weight AI safety. Uh, Users can modify their models, including fine-tune them to do on like unsafe data. Now, we might think, okay, well, why is this a problem? We have like alignment in like post-training today, and like refusal training, and these are all kind of maybe broadly the same thing, but we have existing countermeasures applied that we apply to our pre-trained models to make them into helpful and harmless assistants. Well, let's start with the first motivating question. Like, why not train the models to just refuse unsafe prompts? This is, what we do. Often, if you ask Llama outright about something unsafe, it will refuse. But it's very easy to remove these safeguards. It's very easy to fine-tune an open weight model such that it never refuses or refuses far less often. This is kind of like we refer to this broadly as like tampering with the safeguards. You're like removing them or degrading them in some way by modifying your model. So if there was some dangerous knowledge or a dangerous capability the model has, but you rely on the model just refusing to tell you the answer as your safeguard, if it's easy to remove refusal, then you're in like a quite vulnerable position. Um, and open weight models are becoming like increasingly more capable, which is exciting, but that also means that in the future, it's quite plausible they'll begin to have these dangerous capabilities, and we can't rely on refusal. Second is, why not train the model to forget risky knowledge or try to fine tune away this undesirable knowledge? This is often kind of framed as like a machine unlearning problem and is, to my understanding, not really been yet applied commonly within industry. This is largely a like academic field at this point. But the core problem in unlearning, and this varies somewhat based on the technique you use, but something that the current state-of-the-art techniques largely suffer from is that they suppress rather than remove undesirable knowledge. And this is a problem because when the knowledge is suppressed rather than removed, we will see instances of fine-tuning these unlearned models, even on benign data, or maybe a handful of examples of the unlearning target, and the models will all of a sudden remember everything they had supposedly forgotten. So you can kind of think of post-training broadly as just trying to suppress a capability, but when you have white box access to the model, because you've downloaded it locally and you can modify its weights, it's very easy to elicit all this suppressed knowledge. So this is why today's current post-training safeguards don't really work well, or barely at all, in an open weight setting. All right, so that was the motivation. We talked about that models can learn undesirable capabilities and how current post-training techniques try to suppress these capabilities and aren't great at actually removing them after they've been learned. But in an open weight setting, users can modify the models to easily elicit the suppressed knowledge. I'm going to go through our experiment setup of how we how we studied a potential solution to this problem. And then at the end of this section, I'll do a quick pause to answer some questions. But one other consideration is that although we focus on open weight models as a motivating example in this work, many of these problems also extend to closed weight models. Maybe replace weight modification with like input space jailbreaks. All right. So if we don't feel like we can rely on models on like post-training to like suppress knowledge, it seems like we might need to look at preventing models from learning unsafe knowledge to begin with. So in this work, we study like the very intuitive and surprisingly unstudied for the most part problem of there's a dangerous capability you're worried about. Why not just not train on data related to that capability? That might get you a long way. Um, and this has been unstudied for a number of reasons, which I'll get into at the end. But focusing on our work, we select a specific unsafe or like undesirable set of knowledge, or knowledge that we deem to be undesirable in this work, which I'll flesh out in the following slide. But we largely focus on removing biorisk knowledge from the model, or trying to prevent biorisk knowledge. So what we broadly do is we comb through the pre-training data set, identify the relevant knowledge, remove it, and then the hope is that when we train models on the filtered data set, they have three success criteria, which I discuss at the bottom of the slide here. One, the models that are trained on the filtered data sets should have significantly less biorisk knowledge compared to the baseline model. And our baseline model is the one that was trained without any data filtering. So what this means is that if you remove we attempt to remove all of the biorisk data, um, there should be the model should know a lot less about biorisk at the end of training. The second is that this should be a relatively targeted intervention. We don't want to see notable degradations in general biology or in unrelated knowledge. Um, this can be somewhat of a challenge for like very, for like obvious reasons, like maybe some knowledge there isn't like a clear borderline, or maybe some knowledge is borderline of isn't a clear distinction. But for the most part, we don't want to be seeing like 20-point drops on MMLU, for instance. And thirdly, and most ambitiously, our technique, data filtering should be tamper-resistant. It shouldn't be trivial to fine-tune this knowledge into the model, such that if you fine-tune on a few examples, knowledge shoots back up to the level of the baseline, like what we see with unlearning. It should take a lot of effort and a lot of data to get the models to learn about biorisk because of all the filtering we did. And this is especially useful in the open weight setting. I'll move a little more briskly through the remaining experiment design section because there's lots of slides here that provide useful context. But for some important details, I mentioned that we're talking about like removing biothreat or biorisk knowledge. We measure this using the WMDP, the Weapons of Mass Destruction Proxy benchmark. This is one distinction or subtlety in our work is that we're not filtering for biorisk knowledge directly. We made a decision at the beginning of this project to instead study proxies for this actually unsafe biorisk knowledge. By studying removing data that is like similar in that it's like advanced virology and pathogen research and stuff like that, but is it in itself safe, but resembles actual unsafe knowledge. By focusing on proxies, we don't have to be worried about info hazards. This allows us to be like much more transparent with our paper. If we decided to try to remove a focus on like actual biorisk knowledge, and then we would have been forced to use like private benchmarks. And then I don't know, when we publish the paper, we just have to say, oh, trust us, this works, but we can't tell you anything about our data or much about our technique. So this is and also WMDP is a popular benchmark in the machine learning literature. So this gives us a good like frame of reference. So WMDP is great, but it doesn't measure biorisk directly. It rather maybe measures proxy or prerequisite knowledge. And we are measuring this in like a multiple choice setting, not like agentic, not like in an agentic setting. So we're focusing on like more factual knowledge. All right. So what I alluded to earlier is that we comb through the pre-training data for models and then try to remove everything related to the biorisk knowledge. Pre-trained data sets are like massive. Ours is like large by academic standards, but still like much smaller than what the frontier companies release. And we still have like over 500 million documents that we need to like filter through. It's a lot of work. So we developed this efficient multi-stage filtering pipeline. It's composed of two stages. The first stage is a block list that's around 6,000 key terms that we generated using Llama 3.370 billion. And these are all terms related to the like biorisk proxy knowledge. One distinction, when I mention biorisk, for the most part, I'm actually meaning biorisk like proxies. Um, I omit the proxies for brevity. But anyway, so we have this block list of like lots of terms. And if a document contains two or more key terms from this block list, then it's escalated to this classifier review layer. That's this final stage on the right. And we use a modern BERT classifier. So not an LLM, a relatively small model that's trained to predict whether the current document contains biorisk knowledge or not. This is an efficient approach in that the block list is just a string lookup. This is a CPU-bound operation that's trivial to parallelize. We don't need GPUs for this. So using like some clever optimizations, but not so clever, we can pretty cheaply iterate through our entire data set just using the string lookups. And because what the topic that we're filtering for, biorisk, has this specialized vernacular, we don't, most documents in the data set don't contain any key terms from this block list. So the block list is cheap. It reviews all the documents in the data set, but it only escalates around 10% of those documents. And we probably could have tweaked the block list to such that it could escalate far fewer if we were to optimize more. But since the classifier, which is, although it's a small ML model, it still needs to run on a GPU, since this only reviews the documents flagged by the block list, then it's only looking at 10% or so of our pre-training data. So this is a significant improvement or in terms of like compute efficiency. Um, and measured in flops, all of our filtering led to less than a 1% increase in total training flops. So in terms of like inference costs, it is tractable using this pipeline to comb through all of your pre-training data. Right. And last major point on our experiment setup is we train models from scratch. This is something that's expensive and difficult, but not as expensive and difficult as people might think, and allows us to make like causal claims about the effectiveness of our data filtering. So concretely, all of our models are 6.9 billion parameters based on the Pythia model architecture. They're trained on 550 billion tokens, which is large by academic standards, both this model in terms of its parameter count and data set size, but still like relatively small compared to the frontier. Our baseline model is trained on the unfiltered data set, and then we train multiple LLMs on various filtered versions of this data set, where we like tweak the sensitivity of our filters such that we're removing around 1 to 9% of data. This setup where everything is held constant, except for these like interventions on the training data, allows us to make pretty relatively precise claims about how filtering affects performance. All right. So and just to refresh the success criteria, we want to drop WMDP performance significantly, ideally as close as possible to the 25% random chance accuracy. We want to minimally affect like unrelated or general knowledge, and we want filtering to be tamper resistant. We want it to require a lot of data to begin to match the performance on WMDP of the baseline model. And then one thing I might further claim is that tamper resistance doesn't necessarily mean robustness. Robustness would like suggest that it's impossible to get models to learn stuff. Here we're making the weaker objective, but still ambitious by the standards of the literature, that we want resistance. In our experiment setup, in our setting, pre-trained data filtering seems quite effective. So here in this slide, we talk about in the absence of tampering, just in like capability prevention, how well does data filtering work? So we evaluate WMDP using a couple different prompting strategies in like a multiple choice setting and a closed prompt setting. But on the left here, we report the average. So our baseline model, which is this gray bar, gets a close to 40% accuracy on WMDP. Our weak filter, which is where we use this multi-stage pipeline, that accuracy is about 30%. So like a significantly lower, especially for this like challenging benchmark. And then our strong filter is where we only use a block list. This is like no review layer, so we're removing far more data. To be more concretely, the orange line removes some, or the orange bar here for our weak filter ends up removing something like 3% of our training data. But the strong filter, where we only have the block list and no like extra review layer, this removes around 10%. But what we end up seeing is that there's not that much of a difference in terms of WMDP performance between these two filters, which suggests that our weak filter, where we're using this multi-stage pipeline, is probably better because we're removing less data. But yes, we do significantly drop performance. It's still above the 25% random chance baseline, but we suspect that a part of that performance gap might be some questions that are either mislabeled or like don't necessarily pertain directly to biorisk knowledge. But so it's unclear whether 30% or so actually is like a true floor on WMDP or not. But absolute performance notwithstanding, in terms of relative performance, this is like a significant intervention and seems quite promising. Right. So most techniques, especially in unlearning, will say, "Oh, we regressed the undesirable knowledge, but this came at some like pretty notable trade-off in another metric." However, we seem to not be incurring any significant significant trade-offs here when we for our weak filter. So we use MMLU as our main measure of factual knowledge. And then we use the Pika, Lambda, and HelloSwag benchmarks as like some measures of natural language understanding. And for our weak filter, which has this multi-stage filtering pipeline, we do not see notable differences in MMLU performance. So on the left here, I have the full MMLU, and we also on the right report MMLU without any biology splits, and then with biology splits. And we don't see significant differences. I don't focus on them as much in this presentation, but the brown lines are circuit breaking baseline techniques. And circuit breakers are the current state of the art for capability suppression. And we broadly find in terms of preserving general knowledge that our technique either matches or surpasses this current state of the art. For the strong filter, and this is when we don't have that multi-stage pipeline, we just kind of shoot from the hip and remove anything that contains keywords. We see a larger drop in MMLU and a larger drop in like MMLU bio, but it's still not catastrophic. This surprised me, this finding. I was initially quite worried about overfiltering when we were doing our initial experiments, but it seems to be the case that you can remove a pretty significant amount of the data set, like a few percent, without affecting performance on these popular benchmarks. This updated me, was one of the updates that I made towards the idea that filtering is tractable, if the cost of false positives is relatively low. One limitation I will touch on more later is that although we use popular benchmarks, there could be some benchmark out there that measures some long tail of knowledge, not captured here, that does show some more of a difference between filtering and the baseline. But so like we can make the claim that at least with these popular benchmarks, we don't see anything, but maybe there's like some more niche knowledge where there is an effect. But we don't know either way. All right. So tamper resistance. This is perhaps the more novel and the results that we as a team of authors are the most excited about. So, okay, we've prevented the models from learning this knowledge to begin with. How easy is it to fine tune this knowledge back into the models? And again, we share more experiments and more figures in the paper. This is just kind of skims the surface. But at a high level, we fine tune on a set of 20,000 or so biorisk papers provided by the WMDP benchmark. These are all scientific papers that the multiple choice questions from WMDP are sourced from. So this is perhaps among the most high quality data sources you can find in terms of improving WMDP performance. Our filters are the orange and blue lines at the bottom here, and the gray and brown lines are what we're comparing against. So the first off, one thing that jumps out is notice this like very steep slope for these brown lines here. These are the circuit breaker capability suppression baselines. And this is not a novel finding in our work. Other papers have found similar results. But when you do a fairly minor amount of fine tuning, the circuit breakers kind of get undone. They no longer suppress the undesirable knowledge. So you see performance shoot back up. Whereas with data filtering, or models that underwent data filtering, we do see a gradual increase in WMDP performance, but we fine tune on this data set for 2 epoch, and we still don't see a convergence. There's still a gap between our models and the baseline models. So this isn't full robustness. Performance does improve, but this suggests that an attacker would need a lot of high quality domain specific data, at least in our experimental setup, would require a lot of high quality data to get the models to match the level of knowledge of the unfiltered baseline. So this is quite a success. This is compared to the rest of the literature, this is to the best of our knowledge, a state-of-the-art tamper resistance. All right, so I showed in the previous slide, the instance of where we're fine-tuning on these high-quality biorisk papers, like very information-dense scientific papers. Well, what if we also fine-tune on just some general knowledge, like some Wikipedia? Because other works have found that even like benign fine-tuning, where you're fine-tuning on general text, can break existing capability suppression techniques. And we replicate this finding here. So you see a pretty similar trend in the circuit breaker results. Again, these brown lines here, where you see they shoot back up. And here we're not even fine-tuning on the biorisk papers. This is just some general Wikipedia stuff. Maybe there's like 1 or 2 articles in this whole data set that talks about biorisk or something, but much lower prevalence than the previous data set. But here we find relatively flatline performance of our filtered models. You fine tune on a bunch of general text. It doesn't obviously improve the model's understanding of biorisk. So this is like a good example just to show like how ill-prepared the existing techniques in the literature are handling the in open weight setting. And I don't want to like dunk on circuit breaking too much. It's a really clever technique, and the authors admit that this is like open weight models is not what the technique is geared towards, or it doesn't fit into their threat model. But there really aren't any techniques, except now for ours, that seem to really hold up in the open weight setting under scrutiny. Um, so this is a promising result here that at least for like the very low resource attackers, they don't have access to large amounts of high quality data related to the dangerous capability. Um, it's unlikely they'll be able to elicit this capability easily, like just with fine tuning on general text. So this is almost borderline robustness, it seems. I don't know if I quite feel brave enough to make that claim. All right, so those were maybe there's like 3 main results in our paper. There's that we can prevent capabilities. There's that when we train the filtered models, they're like quite tamper resistant, or at least far more than existing safeguards. And the third and final is these results here. So what you might ask, okay, well, models, especially nowadays, seem to get their information from 2 sources. Their parameters, so like what they learned during training, and information that's provided in the prompt. And this is increasingly common as models become more agentic and are like augmented with like search tools and RAG and stuff like this. Our question was, does data filtering make it more difficult for models to reason, or reason might not be the right word because that might confuse this with reasoning models. Models reason, reasoning models. I'll focus on retrieval. Maybe that's a clearer way to describe this. Um, does this make it more difficult for models to retrieve the information related to biorisk from the prompt? So how we measured this was we created a new version of WMDP where we took the abstracts from various biorisk papers, and we had Claude generate multiple choice questions about these abstracts. Then we performed 2 evaluations. An open book evaluation, where we include the abstract in the prompt, followed by some question about biorisk, where the answer is present within the passage. And then a closed book version, where we just ask the biorisk question, but don't include the context. So the gray line here is our baseline technique the baseline model that was not trained with any data filtering. Our light green is when we just do filtering, And then dark green is when we combine filtering and circuit breaking. So what we find in the closed book setting is our filtered models perform meaningfully worse than the unfiltered model. So this is when they don't have access to the information in the prompt. They just have to rely on the knowledge from their parameters. But in the open book setting, so this middle, especially in this like middle plot, we see like when you provide the passage in the prompt, our filtered models can still do a really good job of retrieving the information to answer the question correctly. Maybe a little bit worse than like our baseline. But it seems to be like quite the case that just because our models are like deeply ignorant of this topic, it doesn't stop them, at least in our like simple evaluation, of being able to extract the answers to various questions related to biorisk. Contrast this with a circuit breaking technique. Circuit breaking trains the model to like not be able to think about biorisk in some sense. That's like a maybe a simplified explanation. But the model can't even think about biorisk. And if it can't even think about it, it can't retrieve the relevant information from the prompt. Again, it's a cool technique that I kind of brush over a little bit in this paper. But as we established, circuit breaking can easily be undone with tampering. So in this right plot here, this is when we tamper and then do our open book evaluation. And we see that like all the techniques begin to perform pretty comparably. Now, one caveat here is this is like a very simple evaluation setup where you can think of it as like perfect retrieval or perfect RAG, where we only have like one piece of context in the prompt that like is the one that contains the answer to the question. In reality, in like real RAG or search deployments, you might have very long contexts where like you have this needle in the haystack problem where like the correct information might be anywhere in this like long context. And you might have noisy like chunks of information. You might have conflicting information. It might be up to the model to decide like what information to search for. And maybe if the model is like ignorant, it doesn't know like what to even search for. Here we like provide the information. So there could be ways that ignorance helps in this like more practical, like real world setting where like our benchmark here is very like synthetic. But if you reduce all those confounders, this result here suggests that if you prompt the model with the information, it can use the information. So this is a limitation of data filtering, or at least like advocates for the idea that you might need a defense in depth. Ignorance alone doesn't handle all threat models. I might run to the end for just the final few slides, and then we will take our questions because I think a lot of the open questions from the previous round are things I'll cover in the next few slides. All right, so in my mind, our results are like quite promising, but they do have like many limitations in open questions. Um, so I touched a little bit on this earlier. We measure this like proxy knowledge, and we measure multiple choice evaluations. This is like perhaps quite different than like real biorisk dangerous capabilities. Often to actually do unsafe stuff in the real world, you're going to need like tool use and agency and long context lengths. The models we train are like quite simple by comparison. The reason that we did this was a pragmatic one. We had 3 months on our compute cluster, which like used up all of our grant money. And we knew we needed to train like at least two models, like our baseline model and a filtered model. But we didn't quite know how many models that we need to do before we like grok data filtering and figure out what a good setup is. So since we didn't know how many models we need to train, we decided to train the minimum viable models that could like get okay performance on these multiple choice exams. We purposefully decided not to expend more of our compute budget to train more capable models or do post training or do models that can reason or do like reasoning or tool use. Um, as it turned out, in hindsight, we were able to arrive at these results with fewer training runs than we expected. So we did have some compute left over, but that's like a bit of just like a pragmatic example of when you do this kind of work and you especially have like a limited time window or a limited amount of like compute that you need to like, or like a fixed compute budget. You need to try to like navigate this ambiguity and like train the minimum viable models. The second is like one of our claims is we don't see any notable regressions in general capabilities or general knowledge. We use popular benchmarks, but there could be some facet of these models that these our benchmarks don't capture that actually does regress or maybe improves. There's like I would not be surprised if someone on Twitter found that on some benchmark filtering actually does hurt performance. That's not captured in the popular ones. And this is just somewhat of a pragmatic thing of like, there's so many benchmarks, it's hard to pick which ones to use, so we just use common ones. Um, and then for filtering as an effectiveness technique, filtering is, in the way that we present it, a pre-training intervention. So you have some challenges that are common to all sorts of pre-training research, even for capabilities improvements. Um, like you have long feedback loops, you train your model, but it's often kind of difficult to predict what the final end performance will be, even if you do have scaling laws. It's often unclear what sort of data wants to filter for. Like we don't do any fancy like data attribution methods or anything. We kind of just train a classifier and then try to trust the classifier. And then like in the absence of and then like filtering doesn't stop the models from retrieving the information in context. And in the absence of tampering in our benchmarks, circuit breaking slightly outperforms data filtering in many settings, but not all. All right, and then before I jump into questions, there's a few more interesting points. Um, well, we show that we're like very pro data filtering, my authors and I, and our paper kind of demonstrates this. But there have been some recent works that are like skeptical of data filtering. So the ones I talk about in this slide are some works that focus on data filtering for toxicity. And like really recommend reading these papers. Like safety pre-training is one of them, and then when bad data leads to good models is another. Excellent papers. I'm going to provide oversimplifications of them, but the main vibe is that um, for toxicity, you probably actually don't want to filter your data. And this is because, or like, data filtering can lead to models that are more toxic. And the main rationale for this is that data like toxicity is like for the most part a pretty simple capability. Like write me a poem comparing this group of people to like this sort of animal. That's simple for most LLMs to do. But what you need to know is like the cultural context of like why comparing this group of people, this kind of animal is like bad or like has all these like cultural baggage. And if you're filtering out all of that, it's more difficult for post-training to train the model to know what sort of data stuff to refuse. Um, Whereas in biorisk, even if the model like has no refusal and wants to be very helpful, if it just doesn't know the knowledge or the capability because it's not in its weights, even if it's trying to be maximally helpful, it's probably not going to be that harmful. Um, so this is an example here where for this sort of behavior toxicity, this might be more within the purview of post-training and alignment rather than something that ignorance or kind of like deep ignorance would help with. And then all this stuff also applies to closed weight models. Also, even if you're not able to tamper with the model's weights, refusal itself is like a pretty fragile safeguard. And all the examples of jailbreaking and input space attacks suggest that even if you're like ChatGPT or Claude, where people can only prompt these models, refusal still is like pretty like a thin defense. And then for future work, yes, and the main questions that we have, and who almost everyone we've talked with has, whether they be independent researchers, people at the frontier companies, et cetera, is how well does this scale? Like it's well and good that we got these 7B models to work. What about 70 or 700? So what my collaborators and I are actively fundraising for right now is to secure compute that will allow us to develop scaling laws for all of the techniques that, or like for data filtering. So train a whole bunch of models and try to predict the trends of like, oh, is it the case that filtering seems to scale well? Or maybe do we need to filter more and more of the data set for larger models because they can learn from fewer examples? If that's the case, that may be some evidence against overly relying on data filtering. But this is all an empirical question. Like we have some hypotheses, but the only way to know for sure is to actually study this stuff. Also, we focus on offensive or on biorisk. because there's some good data sets for this, and it's because what our collaborators at the UK AI Security Institute were especially excited to think about in this work. But we're excited to also study other capabilities. And then what my collaborators and I are spending most of our active time right now doing, like using GPUs for, is trying to figure out how to solve machine learning or solve this like suppression problem. Because data filtering is great, but let's say you didn't do a data filtering, you did filtering it or it didn't work as well as you wished, or a new threat has emerged that you didn't anticipate for when you were deciding what to filter for. We're going to need to have to address all those concerns, we need better machine learning to remove capabilities after the fact. Um, so I'm studying a couple different directions on how to solve this, whether it be scaling existing techniques or studying like new algorithms. And then my closing hot takes might be that it just seems like it'd be a pretty great for safety if model providers had much more control over which capabilities their models have. Um, some model providers might want their models to not have dual use knowledge. Maybe if the models are like interfacing with the public or you don't trust all of your users. For other model providers, where maybe like for one reason or another, they have some extra safeguards or this is a more like limited deployment, they might be fine with having dual use knowledge. Or what we consider to be desirable or undesirable capabilities might change over time. While we study biorisk in this work, we actually we're not that opinionated about exactly what model providers should or should not be removing or filtering for. It just seems like we'd be in a much better world if these were like intentional decisions that model providers and like the community could make, rather than us just doing pre-training and hoping for the best. So that's maybe like one like important maybe philosophical point to make. The second is that it's difficult for the frontier companies to do this kind of research publicly, in part because like to do good pre-training research, you need access or need to talk like about your data and about your models and about your architecture and how you train them. And this is like very sensitive information. So it seems like for the in the near future, at least, unless something really changes, it's up to us as like the community outside of private companies to do this kind of research publicly. Um, and this is becoming more tractable. Training models is still expensive, but each of our training runs only cost around $30,000. GPU prices are decreasing. The tooling is getting better, so training runs are becoming more efficient. And like the research on how to train like data efficient models is also improving. So $30,000 is still expensive, but if you get a grant or you're in like a moderately funded organization, it's quite tractable to do this work. And this is much of a philosophy that us at EleutherAI are especially interested in like propagating through the community. And then lastly, competition in open weight models is intensifying. Open weight models is one of the few areas in generative AI that China has like clearly surpassed the West. And regardless of whether you think this is a good thing or a bad thing, what seems abundantly clear is we're going to have a lot more competition in open weight models. And GPT OSS is an example of this. Um, so if we're having this like competition of increasingly capable models and more of them being released, but we barely have any guardrails at all, that seems like a pretty striking safety concern. So if there is going to be a competition, and there probably will be, we need to focus now on making it as safe as possible. And then this was a collaboration with a lot of excellent folks at EleutherAI, who I was working with at the time, the UK AI Security Institute, and University of Oxford. And Stephen Casper, who's at UKAC and MIT, was my co-first author in this. And he led a lot of the work around our tampering evaluations. And then Stella Biederman was the like senior author advising much of this, along with really invaluable help from all the other authors. All right. And if you're interested in learning more, here's my website. I think lots of these links should be included in the chat. And I'm really excited to hear what people think.